Now that we have our units, our forces, our trig, our axis system, etc., vector addition, now that we have those reviewed, it's time to move on to motion. There are two types of motion that we need to consider. One is a translation. Translation is just a linear motion. So it is a movement from one spot to another in a straight line direction. It might be horizontal, it might be vertical, or it might be at an angle. But as long as it is a straight motion from here to there, that's a translation. There is also a rotation, which obviously involves a circular motion. And it can be either a clockwise rotation, or it can be a counterclockwise rotation. So counterclockwise, I'll abbreviate those as CW and CCW. So it's a rotation in which things are rotating or twisting. When we consider rotations, we refer to them as being moments or torques. I'll probably more commonly call it a moment, but a torque, if you study torques, it's the same thing. A moment is a force, so a force acting on a rigid body that causes rotation. Calculation of a moment is equal to the force times a distance perpendicular, so we have this additional thing to worry about. The distance perpendicular is the shortest perpendicular distance from the force to the axis of rotation. And so if you're opening a door, you come up, you push against the doorknob with a force, the door rotates about the hinges, and so we would be considering what moment is generated by the force acting through the distance, the width of the door about the hinges. Since it is a force times a distance, the units are force is newtons, distance is meters, so the units of a moment is newton meters. Or in the U.S. customary, a force is a pound, a distance is a foot, and so you would think it would be pound feet, which some people use, but more commonly in the U.S. customary units you'll see a foot pounds or potentially inch pounds. So units are newton meters or foot pounds. The sign, as I mentioned, a rotation clockwise, by convention, that is a negative. And so a negative moment. If it's turning clockwise, this will be at a negative moment. If it's turning counterclockwise, the counterclockwise going against the clock, that's considered a positive moment. Okay, so on our forces we had upwards and to the right were positive, downwards and to the left were negative. When we have rotations, when we have moments, a clockwise is negative, counterclockwise is a positive. Okay, so going back to that door hinge example, say we have a door that's 0.9 meters wide. Okay, so this is the distance between the edge of the door and the hinges, and these little circles over here are the hinges. So a person comes up and pushes with a 100 Newton force against the edge of the door rotates, you're trying to open the door will rotate. I'm asking what is the moment at the hinge? So what moment is created by this force acting through this distance? So the moment at the hinge, we take that simple equation, moment is equal to a force times a distance. We have to make sure the distance is perpendicular to the force. In this case, our force is 100 newtons. So 100 newtons. Our distance is 0.9 meters. We have to worry, is that a perpendicular force distance relationship? And we can see yes, those two are running perpendicular. Okay, so we're good. It is a perpendicular distance. And then the last thing to consider, if we push down, the door rotates this way. This way is a clockwise direction, so we can write it as clockwise. Or we could write it as equivalent to 100 times 0.9. Plug it in our calculator, and that will be negative 90 Newton meters. Okay, so we can either write it as 90 Newton meters clockwise or negative 90 Newton meters. Okay, those are both equivalent. Okay, but we know the moment created by this force acting through this distance is 90 Newton meters. What happens if an employee, a person comes up and they don't push, they apply the same force, 100 newtons, but they don't apply it directly perpendicular, head on to the door? What happens if they're working at an angle? And we know that lots of our jobs are not performed in the best postures, that we're working at odd angles sometimes. And so what happens in this case? If we go back and try to calculate that same moment about the hinges, so we're looking at how is this rotating about the hinges here, we have that same force times perpendicular distance, but we see that now the force is not perpendicular to the distance. So we have to do our extra trig stuff where we're resolving the force down into a perpendicular and horizontal. In that case, we know that this 100 Newton force, where the 100 is the hypotenuse, the angle that the 100 Newton force is acting at 30 degrees from the horizontal. We can resolve this into an Fx and an Fy. Fx travels directly through the hinge. It doesn't cause any rotation. Instead, it would cause a compression on the hinges, but we're interested in rotation. We can see that our Fy will cause a rotation, cause this clockwise rotation, and so we want to find the size of this Fy so we can multiply it by, now that it's traveling horizontal to our 0.9 meters, we want to find what the size of Fy is. So Fx times perpendicular distance, that will really be Fy times our distance. Fy is opposite of 30, so that'll be a sine function, and so it'll be 100, the force, times sine of 30 degrees. This will be our force. Our perpendicular distance is 0.9 meters. This will be, again, a clockwise, so it's going to be a negative. Plug that into our calculator, and we come up with a negative 45 Newton meter moment as being the moment about the hinges. Okay, so this solves that problem, but I do want you to note that in the previous problem where the person applied a 100 Newton force directly perpendicular to the distance of the door, the edge of the door, they generated a 90 Newton meter moment, versus this one where a person is working at an angle generated a 45 Newton meter moment. You can see that working at a perpendicular is more work efficient. So they're more efficient. They can generate a higher moment than working at an angle. Okay, so those were external forces. Another example of an external force that has an effect internally will be if you are trying to lift a 5 kilogram barbell, hold that in your hands. So you've lifted up, you're trying to hold it. Your arm wants to rotate, but instead your muscles, your bicep muscles, are contracting to hold this barbell steady. If we want to find out how hard your muscles are working, that's kind of a two-step problem. And so the first step is, what moment is created by this barbell that is causing your lower arm segment to rotate about the elbow? Okay, so our joints, our body segments rotate about our joints. They're connected at our joints. They rotate about the center rotation of our joint. And so we want to find out what is the moment at the elbow created by this 5 kilogram barbell. 5 kilogram, I told you, that is not a force. It is a mass, and so we're going to have to do something to that 5 kilogram to make that a force, because we know that our moment equation is force times perpendicular distance. Okay, so 5 kilograms, you remember from the previous lecture, if we have a kilogram, we've got to multiply it by gravity, and the metric is 9.8 meters per second. This will be our force. Okay, so the 5 kilogram creates a 5 times 9.8 Newton force. That is applied in a downward direction. Okay, so gravity pulls the barbell down towards the earth. As it rotates about the elbow joint, if we didn't have muscles holding it, we'd see that it would rotate this way. So it's causing a clockwise rotation. Okay, so we can put clockwise here, which we know is a negative. Come back, we have our force. We need to find our perpendicular distance. We see the force is right here. It is perpendicular to this distance. The distance is between the center of rotation of the elbow, the center of the hand holding the barbell. And so that's 0.3 meters is our distance. Multiply those together and put those in your calculator. You find that as a 14.7 Newton meter moment that is rotating in a clockwise direction. So we can write it either this way, or that's equivalent to writing a negative 14.7 Newton meter moment. Okay, so that's an external force that generates a moment. But we also know that our muscles are acting internally. So an example of an internal force creating a moment about the elbow will be if our biceps are creating a 40 Newton force, 40 Newton, that'll be our hypotenuse. It's not acting straight up, straight downwards. Instead, our muscles act at angles inside our body, which makes the problems a little bit more complicated. We know that our moment at the elbow, and again about this same elbow, center of elbow rotation, our moment is a force times a perpendicular distance. We see that our distance internally, our bicep muscle is attached 0.05 meters in front of our center of rotation of our elbow, so just the center of our elbow joint. We don't have a perpendicular distance to our force, and so we would go back to our trig here where I've drawn the triangles that if we have the hypotenuse is 40 newtons acting at a 60-degree angle, we can break it into an x component, a y component. If we look at these, our x component will travel directly through the elbow joint. It does not create a rotation. It creates a compression on our elbow joint. That's not what we're interested in right now. We're interested in rotation. And so this y component creates a rotation. Our y is opposite of the 60 degrees, opposite, so we know the opposite is the sine function, and so our force here is 40 newtons times sine of 60 degrees. Our distance is this 0.05 meters, and it is, if we're pulling up, we can see that it is creating a counterclockwise moment, which would be a positive. And so plug that into your calculator. 40 times sine is 60 times 0.05 meters, and we will have a 1.732 or 1.7 Newton meter counterclockwise or positive moment. Okay, so this will be your answer. So we have examples of external loads creating moments. We have examples of internal muscular efforts creating moments. And so going back, an external question here is we have a person, an employee, holding a box. The box weighs 200 newtons, so 200 newtons metric. Which is worse on your back, a small, dense box or a larger, bigger box that still weighs 200 newtons? So both weights are the same, 200 newtons. Which is better on the body? Case A, the small, dense box, or case B, the bigger, larger box, given that they're both the same weight at 200 newtons? Some of you intuitively know that while you're not supposed to hold the load further away from your body, that creates stress on your back, and so a small dense box can be held closer to your body. In this case, she has it resting up against her abdomen, right on her belly. So you probably intuitively know that the small dense box is better. And so let's use biomechanics to prove that. In this case, we're looking at if we took our lower back, and we usually use our L5-S1 joint, our fifth lumbar, first sacral vertebrae, the joint where those two meet. We usually use that as our center of rotation for our back. We're looking at what sort of rotation is caused by the small dense box as compared to the large box. Small dense box, we know our moment at our low back is equal to force times distance. Our force is equal to 200 newtons. Our distance, we center the entire weight of the box at its center of gravity, which is where the hand is holding the box. And we can see that according to this problem, that right below her low back out to the center of the box is 30 centimeters. So our distance is 30 centimeters. We know our units for our moment is Newton meters, so we want to change the 100 centimeters into meters by dividing by 100 centimeters per meter. And so that will be equivalent to 60 Newton meters. 60 Newton meters clockwise. In other words, a negative. So that's A is 60 Newton meters. In part B, we have the same setup. The moment of the lower back is equal to force times distance perpendicular is equal to that same 200 newtons. Now the box has to be held further away, and so the perpendicular distance between the back and the center of the load is now 40 centimeters. So times 40 centimeters. Change the units by dividing by 100 centimeters per meter. That's equal to 80 Newton meters. Again, a clockwise rotation. And so you can see that the moment that the load creates about your lower back is 60 Newton meters versus 80 Newton meters. Okay. The muscles in your lower back are going to have to resist this. So your muscles are going to have to counteract this. And so you're looking, is it better for your muscles to counteract a smaller moment or a larger moment? And you would say, well, smaller. Okay, so the small dense box is the better case. Case A is the better case. We're going to go ahead and stop it before we move on to the third part of the lecture.